Okay. Very good morning to all of you. So I welcome you all for 1 week virtual faculty development program on numerical simulation and analysis with COMSOL Multiphysics. So as today is the second day and we are going to start the first session of second day. So today Dr. Rahul Bhatt sir is going to deliver us the topic COMSOL Multiphysics for teaching application. So before start of the session, I will introduce Dr. Rahul Bhatt sir. So Rahul Bhatt sir has completed his PhD from Indian Institute of Technology, Bombay in 2019, and he is also having the industrial experience in the L&T Limited. So in L&T Limited, he has done work on the low voltage switch gears. Then he has also contributed in the development of servo control system at Bhabha Atomic Research Center. So his area of interest is in low frequency electromagnetic FEM simulation. So today Rahul sir is going to give us the information related to the COMSOL multiphysics for the various teaching application. So I welcome Rahul sir. So on behalf of Swedish College of Engineering and on behalf of all the participants, I welcome Rahul Bhatt sir, and I request Rahul sir to take the charge and enlighten us. Rahul sir.
Yeah, thank you.
Over to you.
Yeah, I'm audible, right?
Yes, sir. Yes, sir.
Okay, I'll share my screen.
Wait for 1 minute, sir. I will make you host.
Okay. So,
okay, sir.
Yeah, everyone here is attending from online, or do we have people who are sitting in a classroom or auditorium also?
No, sir. Everyone is attending online, and we have provided the that COMSOL software to everyone, and as per the requirement, everyone is having that software along with them.
Okay, I'll share my screen. Let me know if my screen is visible.
Yes, sir. Screen is visible to everyone.
Okay. Okay. Thank you for giving me this opportunity. So, welcome to the session on Introduction to Multiphysics Simulations for Teaching and Research. So, my name is Rahul Bhatt and I work as Applications Engineer in COMSOL, India. This is the agenda of the talk. So, I will give a brief introduction to COMSOL Multiphysics. Now, I guess most of you will be familiar with COMSOL. So, I will just go very briefly through the introduction. Then we will have a look at some interesting case studies from industry and from academics and in various places, how multiphysics simulations were used to solve different kinds of problems. Then we will have a look at how modeling is done in COMSOL. So what equations are solved or how they are solved. Then we will have a look at a modeling example to know that when you are doing any kind of analysis of any device, so what should be the approach to take. Okay. Then we will talk about how to use COMSOL for teaching, and particularly the application builder or the app. So how you can use the app for teaching. And then we will have the Q&A. In fact, if you have any questions, you can actually type them in the chat box. So we can take them as we go along. COMSOL multiphysics is basically a finite element method based simulation software. Now, any physics is governed by differential equations, and FEM converts differential equations into a set of linear equations, or you can say matrix equation, and it solves them using numerical methods. Now, any real world phenomena involves multiple physics. And if you want to accurately predict your the performance of your device or the process, then you need to incorporate multiple physics into the simulation. So for example, if you're modeling a motor, so you start with the electromagnetic analysis, and let's say you get the torque, you get the forces, you get the losses. But just that is not enough, because of the losses, there is temperature rise. So there is heating and temperature rise. So you need to perform heat transfer analysis. Now, because of the heat transfer analysis, there will be some thermal expansion and stresses. So to understand that, you will need to perform structural analysis. Now, if you want to study the different kinds of cooling because of fluid flow, then you also need to incorporate fluid flow analysis. So in this way, if you want to predict accurately the performance of your device, you will need to incorporate the relevant physics, all the relevant physics. So for example, electromagnetics, heat transfer, structural, fluid, and so on. Now, COMSOL allows you to couple n number of physics. So that is the strength of COMSOL. And in addition to that, if you want to model your own equations, or you want to incorporate your own phenomena, then you can do the equation-based modeling. Then, in addition to that, you can also, so once you have done the analysis, if you want to optimize the design, now, when you are optimizing a design of a device, then you need to consider many variables at the same time. So there could be different constraints which could be mutually opposite. That, let's say, one parameter increases and your required output increases, but the other parameters increases, the required output decreases. So that kind of you can say conflicting requirements are there. But even then, you can do a multivariable optimization. So using the optimization module. And then you can also integrate your simulations with MATLAB and Excel. And of course, there are CAD tools. So you can incorporate your CAD geometries in your simulation. Next, once you have built the model, the application builder is a unique feature of COMSOL, which allows you to create a customized user interface. Now, this is going to be the focus in this presentation, because in context of academics, it will be very useful to you. So you can explore different ways in which you can use apps for teaching and research, and in fact, even consultancy. So from your model, basically, you can build a customized user interface, which we call an app. So considering a target user, you decide which are the relevant input parameters, you decide the relevant output parameters, the results of interest, and you generate a fully customized user interface. And you can share that user interface, or which we call app, to the target user. So once the target user has the interface, has the app, he can play around with those parameters, run the simulation, and see the results of interest. So basically, the target user need not be a simulation specialist in order to perform simulation. So that is how the app empowers people to do simulations and analysis, but it does not require everybody to be a simulation expert. Now, okay, I'll just go briefly over this. So COMSOL offers a very fully integrated simulation software environment, where no matter what kind of simulation you want to perform, you basically, the workflow remains the same. You need to go through these basic steps. And so in sequence, so you first build the geometry or you import, then you assign materials, you specify boundary conditions, do the meshing, then you perform study steps. Finally, you come to visualization and analysis. Now, once you have built the model, you can use the application builder to create apps. Okay, so now we'll go on to some interesting case studies. Now, this is a case study from Verist Engineering. Now, they wanted to study or analyze the circulation system in a hospital room. Okay, so you want to design the circulation system. So let's say there are inlet and outlet for the air. So how do you place them so that you have the optimum circulation? And whenever you place the inlet outlet, so what is going to be the circulation pattern? So this is important from various points of view. Like you would like to see that, let's say if there are some microbes or particles inside the room, then how they will be going away or being sucked out from the outlet. So that is the kind of study they wanted to see. So uh, they wanted to see the airflow pattern and the bioaerosol transport, which means, let's say if there's a patient, so they modeled a patient like this horizontal block, and you see doctor, okay, and now this point is basically the mouth of the patient, okay. Let's say the patient coughs, then the microbes will be released. So they are modeled using the particle tracing, and this entire circulation is modeled using fluid flow. So they studied what are the circulation patterns. So yes, somebody has a question. Okay, so the first thing is that you like to see the circulation pattern so that you see that what is the vulnerability of people around the patient. So something like, let's say here, the air is going. Does anybody want to say something or question? Okay, so you see the air.
No, sir.
Yeah.
No,
Okay. Okay. So if you have any questions or anything, you please type them in the chat box. So I will have a look at them. We'll go, we'll address them as we go along. Okay. So you see here, the airflow is going up. Okay. Now, so what that tells us is that, okay, so if it directly goes up, then the vulnerability of people around will be minimum. Okay. Or it will be lesser. But if there are vortex patterns, like if there are circulation patterns like this, then that tells us that the vulnerability of people around will increase. So now so that way you can know that what is the effectiveness of the circulation system, or how you should design it so that so the vulnerability is minimized. And the second thing is that, let's say you release this so that those particles are released, the microbes, then how much time is required for the circulation system to suck out all those microbes or all those particles. That is the study which they did in this simulation. So here you can see the probability of microbes. So basically this is the probability of the microbes, microbe or particles being totally sucked out of the system. So you can see it took almost 300 seconds, so 5 minutes. So it's like if a patient coughs here or some microbes are released, then the circulation system will take almost 5 minutes to suck out all the microbes, and then after that everybody will be safe. Okay, so that is the kind of study you can perform using multiphysics simulations. This is another very interesting case study. So where you see people from various various backgrounds have used COMSOL. So this is a master chef contestant who wanted to make basically this dish, fish roll. Okay, this fish roll basically consisted of two layers. The inside was fish and outside was breadcrumbs. Okay, so there were several constraints which he needed to follow. So something like so the frying time was somewhere around 15 minutes, and then sorry, not the frying time. Basically, after the dish was cooked, it was supposed to be presented before the judges after a gap of 15 minutes. Okay, so after cooking the dish, it was supposed to be presented after 15 minutes to the judge. So there were very different kinds of variables which needed to be um, modified or adjusted. So something like what should be the radius or this width of the fish roll, height of the fish roll, how much should be the layer thickness of the breadcrumbs, for how much time should it be fried so that it it remains warm till it is taken to the judges, and so on. So all these kinds of constraints were there. Now you will be surprised to know that now this MasterChef contestant had a friend who was working in, with simulations. So that friend helped him to model this as a 2D. You can see here 2D cross section. So the heat transfer analysis was done, and the frying was modeled like a sorry, like a convection. Okay, like the oil flow was modeled like a convection over this fish roll. So they performed the analysis and they got some counterintuitive results. So it's something like, let's say, if you just without looking at this, if you look at this and you think that, okay, where will be the hotspot of the system, then naturally we might think that it will be in the center, right? But actually the simulation showed that the hotspots are here. There are two hotspots. Now, it's not just that they stopped with the simulation, they actually verified things or validated them using, so they actually inserted thermocouples inside the fish roll after it has been fried. And they measured the temperature and they validated these results with actual experimental testing. And they also found that there are two hotspots, not one hotspot. Okay. So in this way, he could play around with those parameters and get the optimum parameter values so that he could meet his requirements. And finally, this master chef, he won the third place in the master chef competition. So this contestant, okay, using COMSOL. This is another case where you basically you manufacture or make different kinds of products. Now, basically you want consistent quality. Now, consistent quality. So this is a case of manufacturing of rice puffs. Now, you want them to be uniform. You want ideal texture, flavor, and moisture content, and you want consistent. So for that, there are different kinds of, again, the input variables. So these rice puffs were using microwave. So there are various kinds of parameters or variables that you can change, like the amount for the time for which it is heated, the moisture content, the salt level, the ambient temperature, and so on. So, so these people from Cornell University, they performed coupled simulations. So this involved structural, thermal, CFD, RF. So basically RF was there for heating. Okay, the RF energy was incident on this, which basically was the heat source. Then because of the heating, there was phase change and plastic deformation in the material. So it was structural thermal analysis, and to model the cooling, so the CFD was incorporated. So you have this structural thermal CFD RF coupled simulation, using which you can see for different time period how much, so what kind of state the rice puff is in, and this is the simulated. These are the simulated results. So using this, they were able to optimize the input parameters so that they got a consistent quality of output. Okay. Next, we'll have a look at a different kind of user story. So this is user story from FZB Technology, USA. And this is regarding motor simulation or motor design. So they were designing a electro-hydraulic power steering system in which basically the hydraulic fluid which applies torque onto the steering wheel is pumped by a pump basically which is driven by this motor, okay, permanent magnet motor. Now they wanted to study the performance of this system under extreme loading conditions. So something like, let's say if there is a sharp turn, or the wheels are stuck, or the road is rough, then a high amount of torque needs to be applied onto the steering wheel. So the pump has to work harder. So correspondingly, to create a high torque, the motor draws a high current and gets heated up. So to study this, they performed coupled electromagnetic thermal structural analysis. Okay. And in their simulations, they found that under the extreme loading conditions, the stresses in the stator, so this is the stator, you can see, the stresses in the stator exceeded the yield limit of the stator material. So basically, it was the simulations were predicting failure, okay, at extreme loading conditions. So knowing that, they modified the design. They introduced these axial grooves which you see over here, okay, in the stator. So these grooves allow for the safe thermal expansion of the stator, and they keep the stresses under limits at extreme loading conditions. So in this way, they used multiphysics simulations to design a very robust electrohydraulic power steering system. Okay, so these were all the case studies we wanted to discuss. Let me know if you have any questions before we go ahead.
Okay. If any participant is having any question, you can ask the question as per sir's request.
Or you can type it in the chat box, even that is fine. Okay, if nobody has questions, we'll proceed. Then, so now we'll have a look at how modeling happens in COMSOL multiphysics. So what kind of equations are solved, or what is the approach? So basically, any physics is governed by partial differential equations. So here you can see, depending on the phenomena, there are different kinds of equations. So convection diffusion is described using this equation. DC current flow, or you can say charge potential distribution, is described using this equation. So Gauss law. Okay. Electrostatics, this one. Okay. So I mean, different kinds of physics are described by these equations. So modeling the physics means modeling these equations. Now COMSOL solves them using finite element method. So I'll give you a brief a brief overview of finite element method, so that you develop a better understanding. So first, let us understand how the equations are solved. So let's say you want to solve the heat conduction differential equation, partial differential equations. It consists of these three terms. So this is the time derivative, this is the diffusion term, this is the heat source term. So basically, you can correlate any equation with a general form PDE. So something like you see this. So there's a general form PDE interface in COMSOL. Just to give an example. So how we can get this equation from this is that the corresponding coefficients will need to be equated. So something like EA in this case will be 0, because we don't have the second second derivative term here. dA will be rho Cp, okay, from here. Then del dot gamma, this gamma basically is this term. So K dabba T by dabba X, okay, minus K dabba T by dabba Y and dabba T by dabba Z. So this is the gamma. And F is basically this Q heat source, okay. So this is how you can say the formulation happens. Now this is in terms of the equation. Basically, you don't have to do this. COMSOL does this for you. Now I'll just tell you very briefly what is FEM. So let me know just how many of you are familiar with FEM, or it is new to you. Just you can type in the chat box. So let me know if you, how many of you are familiar with FEM? Okay. Please type in the chat box so I'll get an idea. Okay. Okay. Most of you. Okay. Fine. Okay. Some people are new, some people are familiar. Okay. So I'll just briefly describe. So hold on. I don't have. Pen option actually. Okay. Okay. Now it will be fine. So what is done is basically you start with the equation, something like oh, not able to draw. Hold on. Just give me a few seconds. Actually, I'm trying to use the pen so that I can explain. I'm not able to draw actually. Fine. I'll just explain orally. So in FEM, what happens is basically you start with the equation, something like del square V equal to 0, let's say. Okay. The this Laplacian. Okay. So you start with the equation. The entire domain where you want to solve the equation is divided into small elements. Okay. So if it is 2D, it could be triangular elements, or you could have quadrilateral elements and so on. Usually triangular elements are used in case of 2D, and tetrahedral are used in case of 3D. So what is assumed is that the dependent variable, let's say if you're solving for potential, okay, del square V equal to 0. So that the dependent variable is V, and let's say it is assumed to follow a polynomial function within each element. Okay, so within each triangular element, it is assumed that the dependent variable follows a polynomial function, which means V is equal to A plus BX plus CY. Okay, so that kind of polynomial is assumed. Okay, A plus BX plus CY plus DXY. Now, depending on the terms of the polynomial, you can say that it is linear or quadratic or cubic and so on. So within each mesh element, the dependent variable is assumed to follow that polynomial function. So using that, you can say and the entire matrix equation is formed. So the idea is to find the coefficients of the polynomial. So if you assume V equal to A plus BX plus CY, okay. So within each element, you need to find A, B, and C. Okay. So so when you assemble for each, so there are, let's say you have, your domain contains 10. Hello.
12 बजे.
Sorry, are you saying something?
Hello.
Yeah.
All the participants are requested to mute yourself, please. If you are having any query, any question, you can ask the query question by writing in the chat box.
Okay. So yeah. So the idea is to find the coefficients of the polynomial in each element. So let's say your entire domain, 2D domain, consists of, let's say, 10 elements. Okay. Then you'll have 10 such polynomials and correspondingly 10 into 3 unknowns. Okay. So when you assemble this equation, so it becomes basically a matrix equation of the form AX equal to Y. Sorry, AX equal to B. Okay. So A is called the stiffness matrix. X is the unknown. Basically, X is the value of the dependent variable at all the nodes or the vertices of your elements. Okay, so basically when you solve for FEM, you are solving a matrix equation of the form Ax equal to B, and B is are your boundary conditions. Okay, so A is the stiffness matrix, X is the unknown, and B is the boundary conditions. Okay, so after solving Ax equal to B, you get all the x values. So basically the value of the dependent variable at all the nodes or all the vertices of your mesh elements. So that is what it means to solve the FEM. Okay. So once you have got the value of the dependent variables at all the mesh element nodes, okay, uh, the value of the dependent variable at any point x comma y is found using the polynomial function, okay, which you initially assumed. Okay, so that is how the entire field distribution is found using FEM. I hope I was able to convey in a simplified manner. Actually, I would have liked to draw, but I wasn't able to draw. Maybe you can. Okay, I should have used paint. Maybe. Okay. But anyway, if you have any questions, if you want to discuss this, we can take it up even later on. Okay. Now let us have a look at a modeling example. So this is example of a small transformer, 60-watt transformer, whose primary voltage is 230 volts, secondary voltage is 24 volts. It is rated frequency is 50 hertz. So let's say you want to model this transformer and get the different outputs like the output voltage, input current, and so on. Now, what you need to be aware, okay, you need to be aware that whenever you are modeling any device, you need to consider the details which are significant from physics point of view, and you can remove all the details which are not significant from the physics point of view. So here, if you consider that you want to model this transformer, if you model this entire geometry and try to mesh it, the mesh will become very fine and you will have very large number of mesh elements, and it will result in computational complexity, higher computational complexity. Okay. So what you need to do is, from the physics point of view, now let's say you're modeling a transformer. So this is a magnetic field phenomena. Okay. So from that point of view, magnetic fields point of view, you have to remove the parts or the components which don't take part in the physics. So in case of a transformer, you see the magnetic circuit consists of the coils and the core. Now these are insulator terminals which don't take part in the magnetic circuit, so you can remove them. Okay, this mounting flange or bracket, whatever you call it, so this mounting part is also not taking part in the magnetic fields circuit of the magnetic field, so you can remove it. So what you get is just the core and the coils. Okay, now you also have this casing, metallic casing of the core, but that casing is not taking part in the physics. So the magnetic field is just through the core, it's not passing majorly through this outer sheet, so you can remove this casing also. So finally what you have is the core and the two coils. Now in this example, we have simplified these coils, so you can see the coil shape has been changed to round. Okay, now just in this case, so finally you have the core and the coils. So you have kept only the significant parts of your device from the physics point of view, and finally the simulation is done. Okay, now these results are compared to two things. So one is simplified model results, one is this entire model, the results which we got from this entire model, and the third is the specifications of the device. So here you see the inputs to the simulation are the voltage, input voltage, okay, and the, of course, material properties. And the outputs from the simulation are the primary current, secondary voltage, secondary voltage and secondary current. So this is the input, and these three are the outputs from the simulation. So you can see the outputs from the simplified model. So for example, this primary current. is the same what we get from the detailed model. Okay, and these two are also matching, and those are matching with the specification sheet you can see here. Okay, so what this tells us is basically when you model any device, just consider the features or the components which are significant from physics point of view, and that will give you the accurate result. Okay, accurate result enough for your analysis. Any questions till now?
No, sir. No question.
Okay. So now we'll have a look at how you can use COMSOL for teaching, and basically we'll focus on the apps. Apps. So what are applications? So these applications or apps are customized user interface. So once you have built the model, you can choose the input parameters of interest. So for example, these over here, you can choose the results of interest, and you can add the operations, the buttons of interest. So you have the input model, COMSOL model. You use the application builder, and you create this app by adding all these features of interest. Okay, and you can generate this app which looks like this. Okay, now this once the simulation expert has created this app, you can share it with others or anybody basically, then who can work with this app. He can change the parameters, run the simulation, and see the results of interest. Now let's see in academics what all how the apps can benefit you. So in academics, basically you can use the apps for teaching at undergraduate or graduate level. So these apps, simulation apps, will help in the visualization. So particularly you can, as you know, I mean, let's say in case of electromagnetic fields, it's very difficult to visualize. So in this case, these will be very useful. Then for bridging gap between theory and practical. So here you can see the actual theory in application. So you can build realistic models, and you can see how the theory actually translates into applications. Then creativity to curiosity. So you can actually model any device, any phenomena which you can think of, and you can explore it from different points of view. You can change the loading conditions, the inputs, and you can see how the device behaves. And you can have pre-lecture and post-lecture learning, of course. Most importantly, you can learn with fun. Okay, that is the most important thing. Learning is the most effective when it is playful, when it is enjoyable. Now this is example of a tuning fork app. So I'll show you this app. Okay, basically you have a tuning fork, and you can vary the different parameters like the length, the radius, and you can run the simulation and extract the resonance frequencies. You can even listen to it. Okay, I'll just show you the app. So here we have this model of the tuning fork, and using application builder, here we have created an app. So I'll run the app and show you. So here you have the option to choose that the interface is for computer, tablet, or smartphone. So right now it's for computer. So here you see the app. Sorry. Okay. So if you want to change the prong length, for example, I'll make it 80. Okay. Radius, if I want to change, you can. Oh. Okay. Okay, I change this. Then let's say I change this radius. Okay, you can see the radius is changed. So so we change this, and we'll run this, I think. Okay, now So it is computing the resonance frequency of the tuning fork for different length and rate. And you can also listen to the sound. I hope you heard it.
Yes, sir. Yes, sir. We heard.
So this will make it very much fun to learn. So you can use, and let's say you want to change the material, so even you can do that. Yeah, you can hear the difference. Yeah. So yes, you can build such apps. Now we'll proceed. This is an example of tuning fork app. You could also build an assessment app. So here you can see there are different question tabs, and you can see the question over here, multiple choice questions. Okay, so you can build this assessment app, and you can use that for your evaluation. Okay. Now COMSOL has this application builder, which allows you to easily build apps. So you have all these layout templates. Okay, using which I mean, you have standard templates in which you can just drag and drop different buttons, and you can build an app. So, and you can also build app for different platforms, so whether it is desktop, tablet, or smartphone. Okay. Now let us look at some case studies. Any questions till now? Please type your questions, or you can actually, if you have, I mean, if you want to speak out, even that is fine. Okay, we'll then proceed if you have no questions. So these are some case studies of how apps were used for teaching. So this is example from Virginia Commonwealth University. So in this case, so we are talking about the field, electromagnetic fields. It's very difficult to visualize fields and different kinds of fields. So now you have conservative fields like gravitational field or the electric field, where if you go around in a loop, then the net work done is zero. Okay, but you also have curl fields like magnetic field, so which is exactly the opposite or complementary to such fields. So if you want to visualize the different, I mean, the field distribution in case of different devices, like here you can see a capacitor. So the simulation apps are very useful. So Professor Kinsey at VCU used these simulation apps, introduced it into the curriculum so that it combines the simulation lab and hands-on, and it is a good aid for the lecture. Okay, so these apps allow to easily visualize the 3D electromagnetic fields. This is example of, so previous was the capacitor. This is a example of an inductor or a coil. So you can visualize the fields, and of course you can play around with the parameters and see how the fields change. You can see how the inductance varies. So when we have the demo, we'll have a look at one such example. Okay, how we can build a inductor, and we'll build an app out of it. So when you use apps, simulation apps basically, the app can help students to develop better intuition. So they can test various, you can say, what if scenarios, that what if I change this, what if I modify this, and how it affects the field, or how it affects the behavior of the device. So this will help in developing critical thinking and design thinking. So that is how you can make use of simulation apps. This is another example of how apps were used to teach STEM subjects. So you can incorporate these apps in the curriculum, where so this is example of an app which studies the cooling of a water kept in a glass. Okay, due to the air flowing over the surface. Okay. So here you can see the various plots which shows the circulation, you can see circulation, the temperature, the fluid flow. So when you build such an app, you can test various scenarios, like what if the ambient temperature is different, the flow conditions are different, then you can quickly get the results by using such apps. Okay, I think so we have come to the end of the presentation. So we'll go on to the demonstration. So basically, okay, before going ahead, let me know if you have. Oh, we have a question. How can we use PDE in any equations? I'm not very clear. Can you elaborate? So by PD, do you mean to say the mathematics interface or? So the heat conduction equation. So meaning you want to use the mathematics interface to model the heat conduction equation? Okay, so I'll open the interface to show you. So something like, let's say, you have the mathematics interface. In that you have these PD interfaces. So general form PDE. So general form PDE here. So I'll just add and I'll show you. So as I've showed in the presentation, so you have this equation here. Okay. Now you compare this equation with your heat conduction equation, and from that, basically you want to get the coefficients. So as I showed in the presentation, for this, if you put EA equal to 0, so this term will disappear. The heat conduction has just one derivative term, first derivative. So this will become 0. So you need to specify EA as 0. Then DA, basically DA is rho CP, okay, or CP into rho. So you need to input this CP into rho over here, okay, either the numerical value or you can define a parameter like this CP, okay, and rho, let's say rho is the density. I'm just giving arbitrary value, but something like you can specify that over here. So CP into rho. Then this gamma is basically you see this minus ux. Basically, this is the first derivative. Ux means first derivative. Uxx means second derivative. So here you can specify the derivatives. Now, one thing you can do, you can actually change the dependent variable. So rename it. Let's say not u but t. T. Okay. So t. Okay. So now here you see it is changed. So so you can write tx. If you want to write dabba t by dabba x, so this is tx. Dabba t by dabba y, this is ty. Okay. So that is how, and f is your source term. So whatever is the source, you can input it over here. Okay. So now when you specify all these, now this has become equivalent to heat conduction equation. Okay. I hope I have addressed your question.
Sir, that heat source term, it will be same as of our heat source in that heat transfer module.
Okay.
Both will be same now. Here the heat source term and the heat source term from heat transfer in module, because there also their Q term is there.
So you can input that something like you have the heat transfer in solid. See, okay, there's one thing. So if you have a physics based interface for a particular physics, okay, like for heat transfer, then we encourage you to use that physics interface rather than modeling it using the mathematics interface. So it is always advisable that if you have the corresponding physics interface, use that,
Okay.
because that has been customized for that particular application or that particular physics. So in general, this is what I mean, you should be aware of, that if there is heat transfer in solids interface, then it is
Yes.
always advisable that you use this interface rather than modeling it using general form PD or any PD interface.
Okay, so we don't have to use both at one time.
No, 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 not at all.
Okay, thank you, sir. One last query I have.
Hmm.
That in this equation we have seen Q plus QTED.
Hmm.
That QTED is, how can we define this QTED? Because it is something extra from heat conduction equation.
QTD, so usually this, okay, heat source, see here. So heat source, okay.
Yes.
So this Q, this is what you need to specify. So where is the heat source and whatever, how much is it or whatever.
Yes, sir, yes.
Yeah. So that QED would be, I think it will be optional. It's not necessary that it has to be there every time.
Okay, sir. So while mentioning in any research article, we don't have to add this one. We
No,
don't have to show this one.
no, don't have.
Okay, sir. Okay. Thank you, sir.
Yeah, thanks. And just okay, just since you are mentioning it, see whatever are the internal variables. So, for example, the heat source term. So they will be available over here. So maybe I'll just get initial value and so global hold on. Need so heat. Okay, you can see heat source. You're asking, right? So you have those available as internal variables. Okay. So just for your awareness, I'm telling. Okay.
Yes, sir. Thank you.
Should we take a 5 minutes break before we proceed? Yeah. Should we take a break of 5 minutes? Please let me know.
Yes, sir, no problem.
Okay. Okay.
So we'll take a break of 5 minutes, and after 5 minutes, we'll rejoin the same meeting.
Yeah. Yeah.
Thank you, sir.
Hello, I am audible, right?
Yes, sir, you are audible. No problem.
So shall we start?
Yes, sir, no issue.
Okay. Okay. So in this demo, so we'll do this hands-on, right? Everybody will do along with me, right?
Yes, sir, yes, sir.
Okay. So we'll model a inductor, basically a air core inductor, single layer air core inductor, whose parameters are basically the diameter is 50 mm, the length is 100 mm, number of turns are 100, conductor size, wire size is 1 mm cross 1 mm, and the material is copper. So we'll model this simple inductor. Since we have a formula, okay, exact formula to get the analytical formula to get the inductance value, and we'll compare our results from the FEM with the analytical prediction. Okay, so this is the inductance formula for a single layer air core inductor. So L in microhenry is given by d square n square by L plus 0.45 d. So your d diameter is in meters, n number of turns, L is the axial length of the coil in meters. Okay. So using just this simple formula, you can get the inductance of a single layer air core inductor. And this is a very accurate formula. So you can get the inductance value with the error less than 2%. Okay. Then resistance we will get using the normal, our usual resistance formula, rho L by A. So rho is the resistivity of copper, L is the length of the wire, and A is the conductor cross section. Yes, one more thing. So for such a coil, we have an analytical formula which gives us the magnetic field distribution along the axis. Okay. So we'll get these three results, like we'll get the resistance, we'll get the inductance and the field distribution from the FEM, and we'll compare it with these analytical results. Okay. So we'll start with the model. So let us open a new model wizard. So we'll start with 3D. Okay. So 3D. I guess yesterday you had a hands-on session, right? You can actually answer on the chat box. I mean, that will be faster. Okay. So we start with the magnetic fields. Okay. Since we want to model an inductor, we click magnetic fields, add. Now, whenever you click any interface, when you add interface, the corresponding dependent variables are seen over here. So what that does is basically when you add magnetic fields and solve for magnetic fields, the magnetic vector potential components, these are what are solved for. Okay, these are the output. And then from these components, you get all the other variables, like you want the magnetic flux density B, or you want the magnetic field H. So all those are obtained from this magnetic vector potential. Okay. Here we add, let's say, stationary study. So you must be familiar with the interface by now, I guess, because yesterday you had the hands-on. So what we'll do is first, let us define parameters, okay, for the inductor. So go to parameters, first N, number of turns, 100, current I, 1 ampere, L is the length of the coil, which is 100 mm, R is the radius. R will define R, radius of the coil, which is 25 mm. Diameter is 50, so radius is 25. And let us define the thickness of the conductor, which is 1 mm. So our conductor is basically 1 mm cross 1 mm wire. Okay. So now define these parameters. First, so once you have defined these, please let me know. Then we'll proceed. Okay. I'll wait for some few seconds or maybe half a minute, so that all of you can add these. So please let me know once all of you have done this much. You can type in the chat box. So shall we proceed? Okay. So the next thing is we'll draw the cylinder for the coil. So you click this cylinder, and okay, come to geometry, change this to millimeters. Okay, sorry, just this, change this to millimeters. Come to cylinder. Okay, just add cylinder, and here you can specify this. Okay, the first thing is that we'll define it like a surface, not a solid. Okay, because we want basically a cylinder with a small thickness. So choose surface, type here R plus TH by 2. Now I'll tell you why. So our average radius is R, okay, but the outer radius of this surface is going to be R plus TH by 2. So this TH is basically thickness of the conductor. So we add half of it to R, so that we get the outer radius of our cylinder. You type height as L, okay, and we place it in the center. So specify this Z as minus L by 2. Okay, you can click build selected. So you see a surface is formed here, cylindrical surface. It has no thickness. So you see, radius is R plus TH by 2, height is L, Z is minus L by 2. Okay, now we'll give it a thickness. So come to this layers, specify this as TH and click build selected. So here you can see a layer has been formed. Okay. So let me know once everybody has come up till here. Just type in the chat box that you have finished. So let me know. Shall we proceed? Shall we proceed?
Yes, sir, no problem.
Okay. So next you define a sphere, add a sphere. And sphere radius. So I'll tell you a thumb rule. Okay, whenever you are modeling any device, the thumb rule is that the surrounding air domain should be about 10 times the maximum device size. So we'll specify the radius as 5 into L. Okay. So this is so you can follow this thumb rule in case of, let's say, you want to model some electromagnetic device. So the thing is, you will have the device or whatever, inductor, capacitor, whatever, and you also need to have a surrounding air domain to compute the field distribution around the device. So that air domain should have a size of roughly 10 times the device size to get a sufficiently accurate or field distribution. You can have a basically bigger domain also, but 5 or 10 times the device size is enough of a size for the air domain, so that you get sufficiently accurate results without any distortion in the field distribution. Okay, so the geometry is done. Now we'll go on to materials. So you click add material from library. We will add air. Just double click air. So whichever is the first material which you add, by default it gets assigned to all domains. Here you can see. Okay. Now we need to specify copper, but then that will be specified when we model the coil. Okay. So here just air is sufficient. So we have added air to all and assigned it to all domains. Next, we add the coil feature. So you choose this coil. Okay, and you can use the select box, this one, to select all the coil domains. You can see here. So 4 domains are there. Okay, you can select those in the coil. Now come to the settings. Change this to homogenized multi-term. Choose circular coil. And now specify the current as I. Number of turns as N. Here you see coil wire conductivity 6E7. So this corresponds to conductivity of copper. And the conductor cross section area is 1E minus 6. Now in our case, it is 1 mm cross 1 mm, which is 10 raised to minus 6. Okay, so this is what is the conductor cross section. You see, this is the reason why I did not add copper in the materials. Okay, so this coil feature itself, it has this, so it models that the conductor material is copper. Okay, so I'll just repeat. So you add a coil feature, you add all these domains, choose homogenized multi-turn, circular, add current as I, number of turns N, and rest remains as it is. Okay, shall we proceed? So see, here we have chosen circular coil. Okay, so we need to specify a reference edge. So come to coil geometry and you need to choose the edges. Choose outer edges. Okay, so this gives a reference direction for the current flow. I hope everyone has come up till here. Let me know if you can proceed. Shall we go ahead? Okay, so I think we'll go ahead. So we have modeled the coil. Okay, now we come to mesh. Now mesh can be physics controlled mesh, or you can have a user controlled mesh. So right now I'll just click build all. Okay, now if I hide the outer domain, where is it? Then you can see over here that the mesh is quite coarse. Okay, so we'll make it finer. What we'll do is come to mesh, change this to user controlled, then come to free tetrahedral, right click, add size. Then come to settings, change this to domain, add these 4 domains. And just change this to finer. So now you can see this is sufficiently fine mesh. So just I would repeat, change this to user controlled mesh, come here, add size node. In the size node, change this to domain, add all these domains and make it finer. Has everyone finished till here?
Yes, sir.
Okay. So we'll go to study. So this is done basically. So we defined the geometry, we added materials, we specified boundary conditions. So we added the coil, we did the meshing. Now we'll solve. Now this is stationary. So basically this will give us the DC inductance value. Okay. If you want the AC inductance value, I mean at any frequency, you'll need to perform a frequency domain analysis. Okay. But you should also consider that, let's say if you want the inductance at 50 Hertz, then at 50 Hertz, the skin depth for copper is about 9 millimeters. Now, the cross section, this thickness of this inductor is just 1 mm and skin depth is 9 mm at 50 Hertz. So basically this will behave as if it is a DC. Okay. So the inductance with stationary, so what we compute with stationary, it's still going to be valid for an excitation of 50 Hertz. Okay. So long as the skin depth remains greater than the thickness of the conductor, okay, which is 1 mm. So this inductance value will remain. Okay. I mean, it will remain the same. The flux linkage will remain the same. I mean, the current distribution will remain the same. So the flux linkage will remain the same. So the inductance will remain the same. So let's solve this. you should also be aware of one more thing, that when you use homogenized multi-turn coil domain feature, so this feature does not compute the induced currents inside the coil. So basically, you cannot capture skin effect and proximity effect and all eddy current effects when you use the homogenized multi-turn coil domain feature. Okay. So basically, when you use this feature, you have to ensure that the skin depth at your excitation frequency is greater than the conductor cross section thickness. Okay. Okay, so we have solved this. We get the magnetic field. I'll just unhide everything so that we can see. So here you will be able to see the field. Okay. So what we want is the inductance and the resistance. So what you can do, come to derived values, right click, add global evaluation. In this, since we have modeled a coil, we'll get coil parameters. Okay. So in this, you can have these current, inductance, power. Concatenated flux means flux linkage. Okay, this will be very useful for you in general. So if you want to find the inductance from first principles, or if you want to find mutual inductance in some other case, so this is an internal variable which will give you the flux linkage. Okay, so right now we want the coil resistance and we want the coil inductance. So I will add this. Now I will change this H to millihenry, okay, because since I think it is very less, so I'll make it millihenry. So now here you can see the, so if you click evaluate, you'll see resistance over here 0.26 ohms and inductance has 0.198 millihenry. Okay. Now we'll have a look at the results. So we have calculated the resistance and inductance value using the formula which I showed you earlier. So resistance as per the resistance formula is 0.26 ohms. And from FEM we got 0.26 something, okay, 0.261. Inductance, what we got from this formula, this one, sorry, this one is 0.2 millihenry. And from FEM we get is 0.198 millihenry. Okay, so the error is less than 2%. So here you can, I'll show you again, or in fact you also have the results. Resistance is 0.26 and inductance is 0.198 millihenry. So that is the first part. The second part is that we'll plot the magnetic flux distribution along the axis. So I will plot cut line 3D and specify it from minus L to plus L. Okay. Minus L to plus L, plot it. Here you see it. It is along the axis. Okay, minus L to plus L. Now let us plot the magnetic field along this cut line. So you choose cut line 3D one and plot this. You get this distribution. Okay. Now we want to plot the same using analytical formulation. So see, what I'll do is, what I have actually have this already written. So I will copy paste it onto the chat window. So you can copy paste it. Okay. So just copy this expression and here you add a duplicate line graph and just paste it over here. So this is basically this formula which I have shown over here. This one, mu 0 ni by 2l z plus l by 2, and this entire thing, which is written using the internal variables and the parameters. Here you can see n, l, z is the z coordinate. Okay, mu 0 constant is basically permeability of free space. So if I click plot, you can see here now both of them are visible. You can see very close match between the two. If you want, you can increase the line size. You can add markers, cycle. Here also you can increase, and you can, or in fact what we'll do is change this to dashed or something, or dotted. You can see very close match between the two, blue line and the green line. Now the thing is, you might say that okay, this is slightly these things are there, irregularities. So basically you just need to refine the mesh here. You just need to refine the mesh to get a smoother plot over here. Okay, right now we have just refined the mesh of the coil, but the air mesh, I mean mesh inside the air domain, is quite coarse. So that's why this you can see certain discontinuous changes, slight discontinuities. But you can see that there's a very close match between the analytical and the FEM results. I hope, has everyone got this plot?
Yes, sir. We have got this plot.
Okay. So, okay. So, since now, so we were going to have a look at all these three. So, resistance, inductance, and the field distribution. So here I'll just show just once again. So these are the analytical results and these are the FEM ones. So you can see close match. Then see here, I have refined the mesh inside the inductor air domain, and here we get a much smoother plot. Okay, so just to show you that okay, you can get a smoother plot and a very close match analytical and FEM results. Okay. So now what we will do is we'll generate an app out of this. So then you come to home, you click application builder. And here, new form, you click over here, global form. Okay. So you'll get this window. We'll choose basic form. So it has buttons, input and output, and graphics. So you have more templates over here. Ribbon sections, logo sections, and graphics. Tabs, you see tabs are there. Toolbars are there. These toolbars. So, I mean, let's go with the basic one. Click content. Here you see. So inputs, outputs, graphics, and buttons. Three things you need to choose. Now here, let's say I choose N and you click over here. So this will add N to the, see this is the preview of the app. Okay. I add R to this. Then let's say I want to see the resistance and inductance also. I'll add this. Okay. Then okay, let's see what if okay, we'll just okay. So we have added N, R, and this global evaluation. Okay. Now come to graphics. We will add the magnetic flux density now. Okay. If you want, you can add this too. And geometry. Okay, you can add geometry also. Buttons. So plot geometry. Compute study. And we'll also plot this magnetic field. So you have all these over here. You can check. Okay. So these buttons are there. And you have these windows. Okay. So now you click this done. Now you need to adjust these placing of all these. So you can bring it over here. Bring it up. Geometry button, then compute button. And this, you can increase the size of this. You can also increase the size of this. And this one. Oh, sorry. Okay, so just adjust the placing of all this. And once you have done that, you click test applications. Okay, you can see this application over here. So now what we'll do is let's say change this to 30. Change the radius to 30. Change the number of turns to maybe 200. Then first we plot geometry. Okay, here you can do all the graphics operations. So if you want to zoom in, okay. Now we click geometry. You see it changed. We changed this, so it changed. Okay. Now we will compute. Okay, we have the updated results now. So here you can zoom in. You can plot this too. Basically, this is not going to change since, of course, the analytical one also follows the same. Okay. So here you see the resistance has changed to 0.6. Previously, it was 0.26. Okay. So this is how you can create an app, and this you can use it to visualize different fields and different results for different kinds of input parameters. Has everybody got this? Everybody come till here? Let me know by typing in the chat box. Okay. Okay, so then this is what I had for this session. So now if you have any questions, please let me know. If you want to know something or I mean any doubts. Yeah, so let me know if you have any questions. You can unmute. Okay. Can we have such app for every application? Yeah, you can generate an app from any model, any simulation model, and you can customize it to your requirements. So as I showed you over here. So whichever the inputs, outputs you decide. Okay. So whenever you build any model, you have this, you go to home, you have this application builder. Okay. So you can start from new form, you can add then and basically fully customize it to your requirements. Yeah. Any more questions? You can unmute and ask if you need to, or you can type whichever you feel is appropriate. So let me know if you have any.
It is requested to ask any query for the for this particular session.
Good afternoon, sir.
Yeah, good afternoon.
Sir, I have a query related to heat transfer module. Can I ask that one?
Yeah, sure.
Actually, in heat transfer module, I have selected a material having absorption coefficient, two materials having different absorption coefficient. So while applying my heat source, how can we check that it is working or not? Because while simulation, I am getting the symmetric result for that one. Is there any equation is required for absorption coefficient to change the?
Okay, let me see. It's a, I mean, it's difficult to address that without having a look at the model. So
Just you can show me how we can select the absorption coefficient. That will be very helpful for me. If it is, you can say the time dependent absorption coefficient.
okay, let me see. So I'll add a heat transfer in solids, right?
Yes, sir.
Okay. Oh, hold on. Okay. So here you want to add
A heat source.
heat source. Okay.
Yes.
Let's say I choose this. Okay. And what do you want to specify? Heat rate.
Yes, sir. We can give any heat rate.
Okay.
But
And
in my materials,
hmm,
can you go to the materials?
hmm.
So suppose my concern is about absorption coefficient. So first of all, we have to select that absorption coefficient of that material.
No, but absorption coefficient in what context? Meaning you have some radiation incident on that, or
Yes, sir. Yes, sir.
okay, then in that case, the physics itself will be different since you want to consider radiation. So you'll need to this add.
I am using radiative beam in absorbing media. That the fourth one.
Oh, this one.
No, no, no. The last radiative beam in absorbing media.
This
The
one.
last one. Yes, sir.
Okay. So here you want to specify.
I have specified the two layers.
Here you see absorbing medium, and you
Yes.
can specify user defined or from material. So you can choose your absorbing medium, let's say domain, and then you can specify your absorption coefficient. Does that address your question?
But after simulation, in my results, it is showing that both the particles, like you have selected one portion,
Hmm.
and the other portion, it is getting same heats.
Meaning, no, I mean, what is different and what difference is expected?
Yeah, we have selected this particular domain or
Okay.
surface,
Okay.
and we have defined here absorption coefficient something like 10 or 15.
Okay.
So what about the other parts of that material? How it will react on that heat source?
I'm not sure what is the expected output. I mean,
Expected the maximum heat should be on that selected part, and little bit of that heat should be on other part. Like absorption is maximum in this part and somewhat in the other part.
okay, so the temperature distribution, you expect that
Yes,
this
yeah,
absorption
yes, sir.
should be
The
higher.
temperature.
Should be higher.
Yes, sir.
Okay, so yeah, I think we'll need to take a look at your model itself to address that. Maybe you can share your model at support@comsol.com. You can send your query
Okay, sir.
at support@comsol.com. Yeah. Yeah. Any other questions? This is a very good opportunity. Please make use of this opportunity to get your queries clarified. Let me know if you have more questions.
All the participants are requested to ask the queries. Sir, there is one query in the chat box.
How can we improve mesh if its value is less than 0.3? So by 0.3, you mean the quality, I guess, right? Mesh quality. Okay. Yeah, so you just need to refine the mesh. So as we have seen here, if I used physics controlled mesh, the coil mesh was quite coarse. So what you will need to do is basically you refine the mesh. You add a size node, you select the domain where if you see the mesh is coarse, and you change it to finer or extra fine or extremely fine. And let's say even extremely fine is not enough, then you can make it customized. Okay, so you can specify the maximum element size over here. Now right now it is 20, you can make it 2 or 1. So that way you can, so let's say I make it 10. This is going to be very fine. Oh no. This is 20. I'll make it 1. It will take a lot of time. Wait. So see what we can do is, see you can examine your mesh like this. You can see the statistics. Okay. Where is it? Oh, it's yet to mesh. Wait. So I'll just make it as normal. build all. Okay, now I'll see the statistics over here. Here you can see. So this is how the distribution of the element quality is there. Okay, this is number of elements, y-axis, x-axis is quality. So quality should be somewhere near 1. I mean, this peak should be as high as possible. So this is okay. This looks like somewhere between 0.7, 0.8 or something like that. So it will show you the statistics. Okay, average element quality is 0.6. Okay, now if you want to improve the quality, so here you can see this is quite coarse to resolve the current distribution. So I'll make it. So I'll change it to finer. Now I'll again see the mesh statistics. Here you see, now it has changed. Now average element quality is 0.611, maybe okay, slightly improved. So this is how you can change, improve the quality. And additionally, you can have a look at our web page. So there are blogs, basically COMSOL blog is a very useful resource. And you can see different entries on, let's say, meshing. So here you can see best practices for meshing domains with different size settings. Okay, you can have a look at this. So how you can use different features, how you can refine the mesh. Okay. So please have a look at these blogs. These are very nice, very readable articles, very simple articles which will help you. Okay. Yeah, any more questions? Let me know your questions.
Once again, I request to all participants to ask the questions. So one more question is there in chat box.
How to plot analytical, hold on. How to plot analytical and simulation values in COMSOL. I'm not clear about the question. Can you elaborate? How to plot simulation values, which one, in what context? Do you mean to say post-processing, like 2D plots or 3D plots? Can you elaborate on your question? Or maybe you can unmute yourself and just ask the question.
Hello. Hello.
Yeah, please go on.
Good afternoon, sir.
Yeah, good afternoon.
I want to ask, like in one of your graphs, there were two values plotted together, analytical and simulated values.
Sorry, your voice is breaking. Can you repeat?
So in one of your PPT, there were two plots, analytical and simulated values plotted together. So can I plot analytical values and simulated values all together in COMSOL, using COMSOL?
That is what we did in this hands-on, right? See here.
Yes.
You add a line graph over here, and you have what you plot here is mf.norm_b. So this is the inbuilt variable which we get from the FEM, and this is another line graph where we have added our analytical expression over here.
Okay.
Yeah, just copy paste it over here, and you'll get that.
Okay, sir. Okay, thank you, sir.
So here, just to clarify, see, this expression contains the parameters like L, N, which we defined over here. Okay, so these are one of the what we have the variables which are used over here, and in addition you have also Z. So Z is basically the Z coordinate. So this is basically along the Z arc length. I'll change it to expression and make it Z, and this also I'll make the same. Okay, so now you can see over here, this is the Z coordinate. So that Z is basically the Z coordinate along the line. Okay, do we have a PDF file about post-processing? So you can also have a look at this blog articles on post-processing. Okay, graphics window. So you can have a look at these. And yeah, we do have a document on post-processing. So I think we should be able to get this. Essentials of, yeah, this document you can have a look at. Essentials of post-processing and visualization. So we have a handbook. Okay, please have a look at this. This will be very useful. Okay. Any more questions? Let me know your questions. Take this opportunity to resolve all your doubts. So meanwhile, I will suggest you to go through the various resources that we have. So first thing is this learning center videos. So these are videos to which explain the different aspects. Okay, so you can see over here the user interface, creating geometry, 2D, 3D, how to use definitions, materials, physics. So have a look at these videos. This give you step-by-step instructions to how to do modeling in COMSOL. That is one thing, learning center. Then you can have a look at the model gallery here. So you can have a look at these models and you can actually download them. So if I click any model, let's say cable tutorial. So here you can see download the application files. You can have, download them directly. You just need to have the COMSOL access account. Okay. You just need to create COMSOL access account and you can download these. And the best approach for modeling is that whatever you're trying to model, so just go to the application gallery and try to find a model which is closest to your requirement. So something like you're trying to model a motor. So you can search for a motor and let's say you want to model the PMM, okay, here. So you basically start with the model which is there in the application gallery or the library, okay. You start from an existing model and then step by step you modify that so that it goes closer to what you're finally looking for, okay. That is the best approach. So try to find a model in the library which is closest to what you're looking for. You see how it is set up and make step-by-step changes in the geometry, in the boundary conditions, so that you go to the close to the application which you are looking for. So that is the best approach and the fastest approach to simulating your applications. Okay. So for example, here you have PMM 2D. So this is this has the geometry parts, basically templates for motors, fully customizable templates. Okay. So that is one thing. Later on, let's say you can have a look at knowledge base. So this knowledge base basically has different articles on specific queries, like if you want to improve convergence. Okay, improving convergence of transient models. So what you can do if you want to improve convergence? So what setting changes you can use? You can have a look at this. So these are for specific queries, specific errors if you are facing, like you see error messages. So for particular errors, what to do, how to resolve that. So this knowledge base is also very useful resource. Okay, so have a look at that. Here you see articles on using different features, something like you see modeling electromagnetic coils or modeling resistive capacitive devices, using symmetry to reduce model size. You can have a look at these articles. These are also very useful articles. Okay, any more questions? Has everyone understood what is FEM, at least to a certain level of clarity? Okay. Let me know if you have any more questions. You can also have a look at these articles on FEM. FEM versus FEM, for example. Okay. Yeah, let me know your questions.
Is there any further question? Yeah. Sir, in chat box, we are having one question.
How can we add combine two geometries? Now, the question is not very clear, meaning what exactly do you want to do using two geometries? See, you can, if you want to import two geometries in a single model, that is possible. So you can add this, you have this import, okay? So you can import this. Again, you can import, sorry. So you can import several geometries, and let's say you import one, and then maybe you use the move function. So here you have move. So you import and then you move the geometry. So you want to adjust so that the geometries are assembled, something like that. So you can use the move function, you can adjust that, and you can create your assembly. Does that address your question? Okay.
Sir, my last question is, can I ask?
Yeah, sure.
Sir, that meshing part,
Mm.
that as the mesh will be finer and finer, the simulation time will directly increase now.
It will increase, yes.
Because I am using the very fine mesh and my simulation is going up to 4 hours or 5 hours like that.
Okay.
Initially, I was using the coarser meshes. So at that time, the simulation time is maximum up to half an hour. So is it correct? It is directly proportional, I think.
It's not as such directly proportional, but you can say that, see, as the number of mesh elements increase, the number of DOFs, degrees of freedom increase. So your matrix size increases. So
Yes.
that's why the solution time increases. But it's always advisable to see how much refinement is required for your mesh, depending on the physics, or where refinement is required. So it's not necessary that you refine the mesh of each and every domain in your geometry. So something like, if you know that in particular domains the gradients are going to be very high, so in that case you refine those domains. So here in this case we refine the mesh of the coil, not the air. The air is a relatively coarse mesh in this. So from that point of view, you can optimize your mesh. You need not refine everything at the same time.
Okay.
So you can have a look at this these articles actually, meshing. How do you use the optimum mesh? Okay, where do you refine? Where you can keep coarse? Okay. See here, efficiently mesh your model geometry. So where you can use swept mesh, where you can use quad mesh. Okay, improving your meshing with swept meshes. You can have a look at these articles. So always ensure that the mesh is optimized. You don't need to have a very refined mesh. So depending on the physics. Yeah.
Yes, sir. Thank you, sir.
Yeah, and one more thing I would like to tell you. So there's something called as adaptive meshing. Okay, so this adaptive meshing here you have for stationary studies, it is available. So you can add adaptive meshing where what it does is that it will find out. So it will run and it will find out where are the very high gradients are there, and it will refine the mesh at only those places. So this is like automatically it will refine the mesh only where the field gradients are high. So you can try this approach, okay, for your simulation.
Okay, sir. Thank you.
Yeah, you can also read about this adaptive remeshing. Adaptive mesh. So you can, sorry, adaptive mesh. Okay, you can read about adaptive meshing. You see, adaptive meshing for local solution improvement. Here you can see where the gradients are high, it will refine the mesh. You see here. You can see it, right?
Yes, sir.
So please make full use of these blog articles. They have very useful articles are there. Make full, I mean, exploit the blog articles to your benefit. Okay. Yeah. Any more questions?
As the session is moving towards end,
Yeah.
I request that if any question is there, please ask. I think, sir, questions are over. So, first of all, I would like to thanks Dr. Rahul Bhatt sir to have such a interactive session. And definitely we come to know that what actually FEM simulation is and how it can be utilized in electromagnetic field, that too again for the low frequency. again, we have got very much good knowledge that how, if any question arises to us, how COMSOL itself is going to give us a solution. What are the tutorials for that? Then learning material which is available over there. So I'm very much thankful to Rahul sir. So hope that everybody will definitely utilize it. And if any question or query arises when we are solving actual problem, then directly we can write to the COMSOL for our query, and we can get the answer. Sir, thank you very much. And I declare that this first session of second day has over, and we'll again rejoin this meeting at 3 o'clock.
Thank you.
Thank you, sir.